Have you ever picked up a critical safety document, maybe something for work or even study, an audit report or a complex spec, and just felt completely lost in like a sea of acronyms?
Oh, absolutely. SSA, RSNL, FF, MFR, RP. It really does feel like learning a whole new language sometimes.
Yeah, exactly.
And look, every technical field has its jargon, right? But when we're talking about railway safety assurance, ambiguity is just, well, it's dangerous. It's the enemy.
I mean, literally dangerous.
Literally.
Yeah.
We're dealing with systems where lives are on the line. Imagine if the signaling design team and the operations team have slightly different definitions of risk or hazard.
Yeah.
That tiny difference could lead to catastrophic consequences down the line.
Right. So precise language isn't about sounding clever.
Not at all. It's fundamental to making systems actually safer. It's about clarity, consistency.
Okay, so that's exactly what we want to tackle today. Think of this as your shortcut, whether you're maybe an engineering student just starting out or you're in your early career getting into the rail sector. We're going to try and demystify some of this specialized vocabulary, the core ideas behind what's called system safety assurance, or SSA.
Yep, SSA, that's the big one.
Basically, give you the essential guide you need to, communicate effectively, understand risk, and really grasp how safety is proven, not just assumed in the rail world.
And SSA is really the umbrella term for all of that. It covers all those planned, systematic things you do, right from the initial concept through to getting rid of the system years later.
All the actions needed to build confidence.
Adequate confidence, yeah. And crucially, to demonstrate confidence, to show proof that a system, whether it's a product, a service, the whole railway, actually meets an acceptable or tolerable level of safety.
So it's an engineering discipline in itself.
Absolutely. It's about providing verifiable, auditable proof that your railway system is safe enough to run. You're not just hoping, you're proving.
And what stops different companies or even different countries from using these crucial terms differently? How do we get that consistency?
That's where the standards come in. Things like the EN 50126 series for RAMs, ISO 55000 for asset management, and others.
Ah, okay.
These standards exist precisely to enforce that common language, that shared understanding. They prevent errors, inefficiencies, and those dangerous ambiguities we talked about.
Got it. So the standards are the foundation for clear communication. Let's start unpacking this language then, maybe right at the top level. How does a railway organization even get the green light to operate legally?
Right. So when a company wants to become a rail transport operator, an RTO, they first need to prove they're competent, that they know what they're doing regarding safety.
Okay.
And this is where you often hear two terms that sound similar, but are actually quite different. Accreditation and certification. People mix them up all the time.
Yeah, I can see that happening. So if I'm starting a new train company, which one is my actual license to operate?
There would definitely be accreditation. Think of accreditation as the formal thumbs up from the regulator, like the Office of the National Rail Safety Regulator, if you're under the RSNL in Australia, for example.
Okay, the official recognition.
Exactly. It says the RTO as an organization is competent. It has the capacity, the right systems, the right procedures, qualified people to properly manage the safety risks that come with running trains.
So it's a legal requirement defined by laws like the RSNL.
Precisely. It's the RTO saying to the regulator, look, we understand how to manage safety risks systemically, and here's our framework, our safety management system. That proves it.
Okay, accreditation is the big picture sign-off on the organization's capability. How does certification fit in then? Is it smaller scale?
Yeah, certification is much narrower. It's focused on conformance. It's about getting a certificate that proves a specific thing, maybe a component, a process, even a management system meets a particular standard or guideline.
Like a specific piece of equipment?
Right. For example, a supplier might get their maintenance process certified to ISO 9001 for quality, or a new braking system might be certified against a specific technical performance standard, saying it meets the technical rules.
So certification proves a part or process meets the how-to rules.
Correct. While accreditation proves the whole organization has the know-how to manage safety overall, it's the legal permission slip for the operator.
That makes the relationship much clearer. The RTO needs accreditation to run and then uses certified bits and pieces as part of building its overall safety argument. Okay, let's shift gears slightly. We've got the regulatory approval, but how does the RTO build and maintain internal confidence that things are actually safe day to day? That brings us to assurance and audit.
Good question. Assurance is, at its core, about confidence. But it's not just a feeling. It's specifically confidence informed by systematic evidence.
Evidence-based confidence.
Exactly. If you, as a safety engineer, say you have assurance about something, you need to have a defensible, evidence-backed belief that your safety goals or performance targets are genuinely being met. It's the state of being sure because the data, the records, the analysis, it all points that way.
Okay, so assurance is this ongoing state of justified confidence we're aiming for. And the tool we use to check up on that confidence periodically is the audit.
Spot on. An audit is that systematic, independent, and documented process. Its whole purpose is to gather objective evidence to evaluate whether the requirements, the safety criteria you set out, are actually being fulfilled in practice.
Independent is key there, right?
Absolutely. It can be internal, but it needs independence from the direct work being audited. Audits are how you verify that the processes you think are building assurance are actually working as intended. Assurance is where you want to be. The audit is like the independent inspection that confirms you're still on the right track.
Makes sense. Okay, let's connect this to the physical stuff, the actual railway, the tracks, the trains, the depots. When we manage all these physical things, we're talking about asset management, right? Often guided by standards like ISO 550.
That's right. And it's crucial. Asset management is basically all the coordinated activities an organization does to get value from its assets while hitting its overall goals, including safety.
And an asset here is pretty broad.
Very broad. It's anything that has potential or actual value to the RTO. The rails, the trains, signaling equipment, stations, even software sometimes. And the key thing about modern asset management, especially under ISO 55000, is it's a big shift from just doing reactive maintenance.
How so? What's the shift?
Well, traditionally, you might just fix things when they break. Asset management forces you to think about the entire life cycle value. It connects the performance of, say, a specific section of track directly back to strategic objectives, like punctuality or, crucially, safety targets.
So you're asking different questions.
Exactly. You're not just asking, when do we need to fix this? You're asking, what's the optimal time to intervene, repair, replace, refurbish to maximize its value over its entire expected life, say 30 or 40 years, while keeping the safety risks acceptable and the service reliable. It forces a much more strategic long-term view.
Okay, I see. So it's about optimizing the whole life, not just reacting. That life cycle thinking seems really important for overall system safety assurance.
It's fundamental. You can't assure the safety of the system if you don't have a grip on the condition and performance of its physical parts over time.
Right. And managing those assets well sets a high bar for measuring how things are performing, which leads us perfectly into the core metrics used in rail safety.
Okay, so when engineers want to evaluate how well a railway system or component is performing, especially from an operational and safety viewpoint, they often use a group of metrics bundled together under the acronym RAMS.
RAMs, right. I've seen that everywhere. Reliability, availability, maintainability, safety.
That's the one. It gives you a holistic view, moving beyond just does it work, to how well does it work, how often is it ready, how easy is it to fix, and is it safe?
Let's break those down. First up, reliability. What does that mean in a railway context?
Reliability is pretty straightforward conceptually. It's the ability of an item, a train, a signal, whatever, to perform its required function without failing for a specific amount of time, under specific conditions.
So if a train is scheduled for a 1-hour trip, reliability is about its chances of completing that trip without breaking down.
Exactly. It's about consistency of performance while it's running. High reliability means fewer failures during operation.
Okay, crucial. But a system could be really reliable when it's running, but maybe it's often down for maintenance. That sounds like where availability comes in.
Precisely. Availability is the probability that a system or component is actually operational and ready to perform its function when you need it. This could be at a specific moment in time or over a period.
What's the key difference there compared to reliability?
Think about a signaling system again. It might be incredibly reliable. Perhaps it only fails once every 10 years while operating. But if it needs, say, 6 hours of planned maintenance every single night, then during those 6 hours, its availability is 0.
Ah, okay. So it's reliable when running, but not always available to run.
Right. High availability means the system is ready to go when the timetable says it should be. It factors in both unscheduled downtime, failures, and scheduled downtime maintenance.
Got it. And the third part of the RAM trio, maintainability, sounds like it's all about fixing things when they do go wrong, or doing that planned maintenance efficiently.
Correct. Maintainability is about the ease and speed with which a system can be kept in or restored to a working state. This involves things like how quickly you can diagnose a fault, how accessible the parts are, whether you need specialized tools, the skill level required for technicians.
So you measure it with things like mean time to repair, MTTR.
Exactly. If a critical trackside sensor fails, is it a 30-minute fix because it's designed for easy swap out with standard parts? Or is it a 3-day nightmare because it's buried, uses proprietary connectors, and needs a specialist flown in? That's maintainability. It directly impacts operational costs and, of course, availability.
Now, this is interesting because these three, R, A, and M, they often seem like they're in tension, right? You might make something super reliable by making it really complex.
But that complexity could make it a nightmare to maintain.
Oh.
Exactly. Lowering the M. That's a classic systems engineering trade-off.
Or you could add lots of redundant parts to boost reliability and availability.
But now you've got more things to maintain, which could hurt maintainability, unless you design that redundancy very carefully. It might also increase cost and weight.
So it's about finding the right balance, not just maxing out everything.
Precisely. RAM analysis is about optimization for the specific operational context, not just blind maximization of each parameter. You need to find the sweet spot based on cost, operational needs, and critically, safety.
And that brings us to the S. We have RAM, but the standard is RAMs, especially under norms like EN 5 or 126. Why add safety separately? Isn't a system with high RAM automatically safe?
That's a great question, and the answer is definitely no. A system can be incredibly reliable, always available, and easy to fix, but still be fundamentally unsafe.
Can you give an example?
Sure. Imagine a train control system that is rock-solid reliable, never crashes, always available. But maybe it's programmed with braking curves that are perfect for dry conditions, but dangerously inadequate in heavy rain, leading it to overshoot platforms or signals.
Ah, okay. High RAM, but still hazardous.
Exactly. The S for safety forces us to explicitly consider the system's potential to cause harm, injury, or death. It ensures that freedom from unacceptable risk is treated as a primary requirement, potentially overriding other performance goals if necessary. Safety is paramount.
Okay. And when we need to get really specific about the safety requirements for critical functions, especially things like signaling or automatic train protection, that's where safety integrity level, or SIL, comes into play.
Yes, SIL is probably one of the most talked about and sometimes misunderstood terms in railway safety assurance, particularly for control systems.
So what is it, fundamentally?
It's a discrete level, usually numbered 1, 2, 3, or 4, that corresponds to a required range of safety performance for a safety-related function. SIL 4 is the highest level, SIL 1 is the lowest.
And what does that level actually mean? Higher SIL means safer.
It means you need a higher degree of confidence that the safety function will perform correctly when required. It dictates the required rigor of the design, verification, and validation processes.
So how does that translate to our hypothetical transit line?
Well, for a function like the core automatic train protection system, the thing that absolutely must prevent trains from colliding, you'd almost certainly be looking at SIL 4. Failure there could be catastrophic.
So that demands extreme measures.
Yes. Things like multiple independent processors, diverse software, extensive fault detection, and fail-safe mechanisms, rigorous testing, formal method perhaps, the whole 9 yards to build that extremely high level of confidence.
And SIL 1.
SIL 1 might be assigned to a less critical safety function. Maybe something like ensuring indicator lights on a control panel work correctly. A failure there is undesirable, maybe causes delay, but isn't likely to lead directly to a major accident. The required level of rigor to achieve SIL 1 is significantly lower than for SIL 4.
So engineers don't just pick a SIL level out of thin air.
Absolutely not. It's determined through a formal risk assessment process. You look at the potential consequences of the safety function failing and how often that failure might be demanded or occur. That combination of severity and likelihood points you to a required SIL level according to defined tables or matrices in the standards.
So the SIL quantifies how trustworthy a safety function needs to be based on the risk it's controlling.
That's a perfect way to put it. It quantifies the necessary risk reduction. Okay, so we've talked about measuring performance and quantifying safety targets with RAMs and SI. Now let's shift to the active processes engineers use to actually find and deal with potential dangers before they cause problems. This is the hazard analysis toolkit.
Right, hunting for danger. But first, we need to be crystal clear on two fundamental words that often get muddled: hazard and risk.
Yes, this distinction is crucial. It sounds basic, but getting it wrong undermines the whole process.
Can you give us a simple way to remember the difference?
Okay, think of a wet floor in a station concourse. The puddle of water itself is the hazard. It's a condition with the potential to cause harm. Someone could slip.
Okay, the water is the hazard. What's the risk?
The risk is the combination of two things. The likelihood of someone actually slipping on that puddle, which might depend on how big it is, how busy the station is, if there are warning signs, and the severity of the consequences if they do slip, minor bruise, a broken hip, etc.
So hazard is the source of harm. Risk is the measure of that harm actually happening.
Exactly. You manage the risk, often by controlling the hazard, cleaning up the puddle, or reducing the likelihood, putting up signs, barriers, or mitigating the consequences, maybe having soft flooring, unlikely.
Yeah.
You can't always eliminate the hazard, but you aim to reduce the risk.
And this is done systematically through the hazard management process.
Yes, typically it follows a few key steps. First, hazard identification. You brainstorm and list everything that could potentially cause harm. Be thorough. Assessment. This is where you analyze the risk. Figure out that likelihood and consequence for each hazard. You evaluate whether the risk is acceptable or needs treatment.
And you fix it.
Step 3, mitigation and controls. You implement measures, design changes, procedures, barriers to reduce the unacceptable risks.
And you're done.
Not quite. Step 4 is ongoing monitoring and review. You have to check that your controls are working and periodically reassess because things change, equipment ages, procedures drift, new hazards emerge. It's a cycle.
Okay, that makes sense. Now, for that crucial assessment phase, engineers use a whole bunch of acronym-heavy analytical tools. Let's talk about some key ones, starting with FAA or FMEA.
Right. FMEA stands for Failure Modes and Effects Analysis. It's a very systematic, bottom-up technique. You take a component, say a specific sensor on the train door,
Okay.
and you ask, how could this sensor possibly fail? Those are the failure modes. Maybe it fails stuck on or stuck off, or gives an intermittent signal or drifts out of calibration.
We'll list all the ways it can break.
Exactly. Then, for each failure mode, you analyze the effects on the next level up, and ultimately on the whole system and the passengers. What happens if the sensor fails stuck on? Does the door stay locked? Can the train move?
So it helps you anticipate the consequences of component failures.
Precisely. And then FMAA adds the C for criticality analysis.
What does that bring?
It adds a layer of prioritization. You assess the criticality of each failure mode, usually by considering its severity, how likely it is to occur, and how easily you can detect it before it causes the ultimate effect. Often this is combined into a risk priority number, or RPN.
So FMEA tells you what could fail and how. FMEA tells you which potential failures you should worry about most.
That's it. FMEA helps you focus your mitigation efforts on the highest risk failure modes. Maybe a certain processor failure is very unlikely but totally catastrophic and hard to detect FMEA flags that as needing urgent attention.
Okay, so that's bottom up. What about the other way around? I've heard of fault tree analysis, FTA. That's top down, right?
Yes, FTA is deductive. You start with an undesirable top event, something you really don't want to happen, like uncommanded train acceleration.
The big accident scenario.
Right,
Okay.
and then you work backwards using logic gates, A&D gates, and OR gates to map out all the possible combinations of lower-level failures, component failures, software errors, human errors, that could lead to that top event.
Can you explain those gates quickly?
Sure. An OR gate means that any one of the inputs below it is enough to cause the event above it. For example, loss of braking might happen if there's a hydraulic failure or an electrical control failure.
Okay, either one is bad enough.
Yep. An ND gate means that all the inputs below it must occur simultaneously for the event above it to happen. For example, a specific type of collision might require signal passed at danger and automatic train protection fails.
So you need multiple things to go wrong together.
Correct. FTA is really powerful for understanding how different failures combine and for identifying potential single points of failure or areas where you need more redundancy or protective layers. It helps isolate root causes.
Okay, switching gears a bit. There's another technique that sounds more like a team workshop. HAZOP, Hazard and Operability Study.
HAZOP is very different in feel. Yes, it's a structured brainstorming technique, usually done by a multidisciplinary team, designers, operators, safety specialists, maintainers.
And what are they brainstorming?
They systematically examine a design or a procedure, section by section. They use specific guide words like no, more, less, as well as part of, reverse, other than, and apply them to process parameters relevant to that section.
Parameters like?
Things like speed, pressure, flow, voltage, time, sequence, data value. For instance, looking at a signaling system design, the team might ask, what if the train speed is more than intended at this point? Or what if the signal command is reverse of what's expected? Or what if part of the safety data packet is missing?
And they explore the consequences of those deviations.
Exactly. They identify potential hazards and operability problems that might arise from deviations from the design intent, not just from simple component failures. It's particularly good for complex process systems, and there's a variant, CHSUP, specifically for computer and control systems.
Sounds very thorough, good for catching subtle interaction issues.
It is. It really leverages the collective expertise of the team to proactively find problems before they're built in.
Now, before you get into all this super detailed FMEA or HAZOP, presumably you need an initial look, something earlier in the project.
Definitely. That's the role of the preliminary hazard analysis, PHA,
Hmm.
which often feeds into a hazard analysis report, or HAR.
Preliminary, so early stages.
Very early,
Mm.
often in the concept or feasibility phase, before you even have detailed designs. The PHA is a broad brush exercise to identify the major potential hazards associated with the proposed system concept, its functions, and its operating environment.
Like what?
Things like potential for electric shock, fire risks, collision hazards, risks of falls, derailment potential, the big categories. It helps ensure the fundamental concept isn't inherently unsafe before you invest heavily in developing it. It sets the scene for the more detailed analyses later.
Okay, initial high-level check, one last tool. Interfaces seem like a classic place for things to go wrong. Is there something specific for that?
Yes, and it's critical.
Yeah.
The Interface Hazard Analysis, IHA. As systems get more complex and interconnected, especially with integrating new tech with legacy systems, the interfaces are where hazards often hide.
The joins between different parts.
Exactly. System A might work perfectly on its own, System B might work perfectly, but the way they communicate or interact, the interface might be flawed. The IHA focuses specifically on identifying hazards arising at these boundaries.
Like connecting new signaling to old track switches.
Perfect example. Maybe the data format is slightly different, or the timing assumptions don't quite match up, or there's an unexpected electrical interaction. The IHA drills down into those connection points to ensure they're safe. It's vital for preventing integration failures. So we've got these great tools, but they aren't just used once. Safety isn't a one-shot deal. It has to be managed throughout the entire life of the railway system. That requires thinking in terms of a life cycle concept.
Right. The idea that a system evolves from the initial idea through design, build, operation, maintenance, upgrades, and finally decommissioning and disposal. Standards like ISO 15288 often frame this.
Exactly. And the key insight is that each phase of this life cycle presents its own unique safety challenges and requires specific safety activities. What you do for safety during concept design is very different from what you do during midlife upgrades or disposal.
And where does it all begin? What's the very first safety-relevant document?
Often, it's the operational concept document, OCD, or something similar. This is that initial, high-level description, maybe text and graphics, of what the system is supposed to do, who will use it, where it will operate, and under what conditions.
Why is that so critical for safety?
Because it sets the fundamental boundaries and assumptions. If the OCD for our new transit line says it's designed to operate only between, say, 0 and 40 degrees Celsius, then every subsequent safety analysis, every design choice, must respect that boundary. If someone later tries to run it at -10 without reassessment, the original safety case might be invalid. The OCD establishes the baseline operational intent.
Okay, baseline set. Now, once we have a design based on that concept, we need to make sure we built it correctly and that it actually does what it's supposed to do safely. This brings us to that famously confusing pair, validation versus verification.
Ah, yes, the V&V question. This trips up so many people. They sound similar, but they answer two fundamentally different questions.
Let's try that bike analogy you mentioned earlier. How does that work?
Okay, imagine we're building a super high-tech, custom racing bike for a specific cyclist. Verification is checking the bike against the blueprints, the specifications.
Did we build the bike right?
Exactly. Does the frame weigh precisely 7.2 kilograms as specified? Are the gear components the exact model number listed in the parts list? Did we follow the assembly instructions correctly? Verification is about confirming conformance to the stated requirements. It's an internal check against the plan.
Okay, checking against the specs. What about validation then?
Validation is asking, did we build the right bike? Does this bike, now that it's built, actually meet the racer's needs and allow them to perform well in their races?
So it's about fitness for purpose.
Precisely. We might have perfectly verified that the frame weighs 7.2 kilograms, meeting the spec. But if it turns out the racer actually needed a 6.5 kilogram frame to be competitive in mountain stages, then the bike fails validation. It doesn't fulfill its intended purpose in the real operational context, even though it was built exactly right according to the flawed spec.
So verification is, did we build it right? And validation is, did we build the right thing?
You got it. And you absolutely need both for safety assurance. You need to verify that your safety features are implemented according to their specification, and you need to validate that those features actually achieve the necessary safety in the real operating environment.
Okay, that distinction is much clearer now. So our transit line project moves along, it gets built, verified, validated, and starts operating. But things change, right? Software needs patching, suppliers change parts, maybe regulations get updated. How do we manage those changes without accidentally breaking the safety we work so hard to build?
That is the critical role of configuration management, or CM.
Configuration management, keeping track of everything.
Essentially, yes. CM is the whole set of coordinated activities used to direct and control the configuration of an asset throughout its life cycle. Every important component, every piece of software, every technical document has a defined, approved state, its configuration baseline.
And CM ensures nothing changes without approval.
It ensures that every proposed change is properly identified, documented, evaluated for its impact, especially on safety, approved or rejected, and if approved, implemented in a controlled way. And the resulting configuration is recorded.
What happens without good CM?
Chaos. Basically, you get uncontrolled changes, version drift, engineers making undocumented tweaks that might seem like a good idea locally, but could have disastrous unintended consequences on the system's overall safety integrity. You lose traceability, you lose control, and your safety case becomes invalid.
So who holds the keys? Who gets to approve or deny these changes to ensure safety isn't compromised?
That's typically the job of the CCB, the Configuration Control Board.
A CCB. Sounds important.
It is. It's usually a formal group made up of key stakeholders, senior engineers, safety managers, operations representatives, maybe maintenance leads. They are the gatekeepers.
So if an engineer wants to update the train control software,
They can't just do it. They have to submit a formal change request, or CR, to the CCB. The CR details the proposed change, the reason for it, and crucially, an analysis of its potential impact, including safety implications.
and the CCB reviews this.
Yes.
Yeah.
They'll likely consult the hazard log, maybe require further analysis or testing, and then make a formal decision. Approve, reject, or approve with conditions. The CCD process ensures that changes are managed rigorously and don't introduce new, unacceptable risks into the operational system. It maintains the integrity of the safety baseline over time.
Okay, we've covered the standards, the metrics like RAMs and SIL, the analysis tools like FMEA and FTA, and the lifecycle controls like CM and the CCB. Now let's talk about the people who do this work, the key documents they produce, and the ultimate legal requirement that underpins everything.
Right, the human and documentary elements are crucial for making SSA actually happen. Let's start with the key role, the SSA practitioner.
What does this person do? Are they like the chief safety engineer?
Not exactly chief of everything, but they are the specialist engineer who really understands and manages the process of system safety assurance. They're experts in the SSA methodologies, RAMs analysis, maybe human factors too.
So they run the process.
They ensure the overall SSA process is adequate and correctly applied across the project or system. They make sure the FMEAs are done properly, the hazard log is maintained, the verification validation activities meet the requirements. They're the process guardians.
Do they need to know every technical detail of the railway?
Not necessarily deep specifics of every single bit of kit. They rely on subject matter experts, or SMEs, for that deep technical knowledge. The signaling expert, the rolling stock engineer, the power systems guru. The SSA practitioner integrates the inputs from the SMEs into the overall safety argument. They orchestrate the safety effort.
Okay, so the SSA practitioner works for the railway operator or the project building the system. But safety needs objectivity, right? How do we avoid them just, marking their own homework?
Excellent point. That's the essential role of the independent safety assessor, or ISA.
Independent, so someone from outside.
Yes, typically an external third-party individual or organization with recognized expertise in railway safety and assessment. They are brought in specifically to provide an objective, impartial review of the safety assurance work done by the RTO or project team.
What are they looking for?
They scrutinize the entire safety case being developed. They check if the processes were followed correctly, if the analyses, FMEA, FTA, etc., are sound, if the evidence supports the claims, if the arguments are logical and complete, and if the system meets the required safety targets like the SIL levels. They provide that critical external challenge.
To ensure credibility.
Exactly. The ISA process adds a vital layer of objectivity and gives regulators and the public confidence that the safety claims are robust and haven't been subject to internal biases or pressures.
And what's the outcome of the ISA's work?
They produce the ISAR, the Independent Safety Assessors Report. This document summarizes their assessment findings. It will highlight any areas of concern, nonconformities, or issues that need to be resolved before the system can be considered safe for commissioning or operation.
So clean ISAR is pretty much essential for getting regulatory approval.
For any major new system or significant change, yes, it's a critical piece of evidence in the final safety acceptance process.
Okay, let's talk about the paperwork itself. We mentioned the hazard log earlier. That sounds pretty central.
It absolutely is. The hazard log is probably the single most important living document in the entire SSA process. Think of it as the master ledger of all identified hazards for the project or system.
What does it track for each hazard?
Everything. For every hazard identified, it records a unique ID, a clear description, the initial assessment of its risk, likelihood and severity, the control measures put in place to mitigate it, references to the evidence proving those controls are effective, like test reports, who is responsible, and the final, residual risk status after controls are applied.
And it's living.
Yes, because it's updated constantly throughout the entire project lifecycle. New hazards might be found during testing, controls might need changing, risk levels might be reassessed. The hazard log provides the complete, traceable history of how every known hazard has been managed. Losing it or letting it become outdated is a major failure.
Okay, the detailed history. And what's the final big document that pulls everything together to make the overall safety argument?
That's the safety case, sometimes also called a Safety Assurance Report, or SAR.
The safety case. This is the ultimate proof.
Essentially, yes. It's the comprehensive, structured argument, supported by evidence, that demonstrates that the railway system, or change, is adequately safe for its intended purpose.
What kind of evidence goes into it?
It synthesizes everything. It references the hazard log, summarizes the results of the safety analyses like FMEA and FTA, includes the verification and validation results, presents the RAMS arguments, discusses operational procedures, includes the ISAR, and explains how the required safety targets, like SILs, have been met. It's a complete package presented to management and the regulator to justify putting the system into service.
Wow, sounds like a massive undertaking.
It absolutely is for complex systems. It requires rigorous effort throughout the life cycle.
You mentioned earlier the SSA practitioner needs expertise in human factors, HF. With all this focus on technology, SIL levels, hardware failures, why is the human element still so vital?
Because railways aren't just technology, they're socio-technical systems. Humans design them, build them, operate them, maintain them, and manage them. And humans make errors, have limitations, and interact with technology in complex ways.
So you have to account for people in the system.
Absolutely. Human factors integration, HFI, means systematically considering human capabilities, limitations, and behaviors throughout the design and operation. A technically perfect system can be rendered unsafe by a poorly designed user interface that confuses an operator under stress, or a maintenance procedure that's too complex to perform reliably in the middle of the night.
So HFI tries to prevent human error.
It tries to design the system to be resilient to human error. It aims to make it easy to do the right thing and hard to do the wrong thing. It considers workload, training, procedures, communication, the design of workstations, alarms everything about how humans interact with the technology. Ignoring human factors is ignoring a massive source of potential risk.
Okay, makes sense. Finally, let's talk about the legal hammer that drives a lot of this, especially under frameworks like Australia's Rail Safety National Law, the principle of SFIP.
Yes, SFARP so far is reasonably practicable. This is a really important legal concept. It's not just a guideline, it's a legal duty imposed on rail operators and others with safety responsibilities.
What does it actually require them to do?
It requires them to eliminate risks to safety, SFARP. If it's not reasonably practicable to eliminate a risk, then they must reduce that risk, SFARP. The goal is to get the risk down as low as reasonably practicable, or ALARP.
Okay, ALARP. I've heard that too. How is SFARP or ALARP different from just making a risk tolerable? Companies often talk about risk tolerability criteria.
This is a critical distinction, especially legally. Risk tolerability is often an internal benchmark set by an organization, maybe based on societal norms or company policy,
a level of risk they are, in principle, prepared to live with.
But SFAP goes further.
Yes, SFARP is an objective legal test. It requires you to consider what is practicable to do to reduce the risk further. You have to weigh the level of risk against the sacrifice involved in reducing it further, things like the cost, time, effort, and technical difficulty of implementing additional controls.
So even if a risk meets your internal tolerable level.
If there's another reasonably practicable control measure available that could reduce the risk further, and the cost or effort of implementing it is not grossly disproportionate to the safety benefit gained, the law, SFARP, generally requires you to implement it.
Can you give an example?
Let's say our transit line has a level crossing. Through analysis, the operator determines the risk is technically tolerable according to their internal rules. But then a new, proven, relatively affordable technology emerges, maybe advanced radar detection, that could significantly reduce the collision risk at that crossing.
Okay.
Even though the risk was already deemed tolerable, the SFARP duty compels the operator to evaluate this new technology. If implementing it is reasonably practicable, cost isn't astronomical, it's technically feasible, etc., they likely have a legal obligation to adopt it because it pushes the risk down further towards that LRB level.
So SFARP forces continuous improvement, pushing beyond just acceptable if better is reasonably achievable.
Exactly. It's a dynamic legal standard that reflects evolving technology and societal expectations about safety. It's a much stronger driver than just meeting a fixed tolerability target.
Yeah.
Hashtag #outro. So we've covered a lot of ground today, weaving through this essential language of railway safety. But hopefully you can see how all these pieces fit together. It really is a system.
Yeah, you've got the foundational concepts like accreditation and assurance giving the structure,
The metrics like RAMS and CEL setting the quantifiable targets.
the analytical tools like FMEA, FTA, AGESOP being used to actively find and assess the risks.
The crucial documents like the hazard log and the safety case, providing that traceable, auditable proof.
And underpinning it all, that legal and ethical driver of SFARI demanding continuous risk reduction.
It truly is a specialized subdiscipline of systems engineering dedicated to proving safety.
And for you listening, whether you're that student starting out or already working in the field, getting comfortable with this terminology isn't just about passing exams or ticking boxes.
Not at all.
It's about being able to genuinely participate in the safety conversation. It means when you're in that CCB meeting discussing a change or you're explaining your analysis to an ISA, you can communicate clearly, understand the implications, and actively contribute to making sure our railways are as safe as they possibly can be.
It's about professional fluency in the language of safety.
Exactly. So to leave you with something to think about, a bit of a provocative thought, perhaps.
Okay.
We've talked about standards like EN 50126 and the traditional ways we assure safety, often developed for bespoke, relatively fixed function systems. But railways today are increasingly using complex commercial off-the-shelf COTS software, maybe even AI, for things like predictive maintenance. These systems can be like black boxes, constantly updated by vendors.
That's a huge challenge, yeah.
So the question is, how do these COTS systems, this complex, perhaps opaque software, challenge our traditional ideas of validation and assurance? If you can't fully audit the code or predict every future update's impact, how do you provide that rigorous, verifiable proof of safety that underpins the entire SSA philosophy?
That's something the industry is actively grappling with. How do you assure safety when you don't have full design transparency?
Something to mull over as you dive deeper into the fascinating world of railway safety assurance.